Welcome to the third part of lecture 4. This is going to be the concluding lecture for unit 3. In this lecture, we are going to look at servo design, introduction of the reference input by feed-forward control. Now, what we have done till now, as far as controller design is concerned, is that we took a plant that was controllable. It was given by x dot is equal to ax plus bu, y is equal to cx. And we designed a control law given by u is equal to minus kx. And when we did this, we basically placed the poles of because the equation that we got for the system after we did this was x dot is equal to a minus bkx. So we placed the poles of a minus bk according to our choice and got the response that we wanted. Now I hope that you could see that this x dot is equal to a minus bkx, the resultant plan that we got, was not responding to any input term. It is basically responding only to initial conditions, because it is similar to the equation x dot is equal to ax, where there is no input term. So this is called the state regulator design, in which you are basically trying to ensure that your system is stable for any initial condition and all initial conditions decay to 0. Because when you try to solve this, if you remember, the solution for this homogeneous state space representation of a system was xt is equal to e to the power at x0. And if your a has negative eigenvalues, that means the system is stable. This ensures that xt tends to 0 for all values of x0. So in a similar way, when the resultant equation that you get for your plant is x dot is equal to a minus bkx, the solution for this would be xt is equal to e to the power a minus bk t x0. And naturally, because you want stable behavior, this means that xt would tend to 0 for all x0, because you have ensured that a minus bk has eigenvalues on the left half plane. And this is how we actually, in the second lecture perhaps, we saw that we could stabilize an unstable system. That an unstable system with an initial condition would have given an exponentially increasing response, could be stabilized if you use the state feedback law. But this is not the general control problem, because your system does not respond only to initial conditions. This is not the only thing that you want. It generally responds to inputs, and you basically require that your system settles down to some point where it is actually tracking an input. So the basic general control problem, which is called the servo problem, is that you want the output at steady state to be equal to some reference input R. This is what you want. In addition to the system being stable and other things, you also want the output at steady state to be equal to some R. You can understand this as, say for example, you give a step input to the system, and you require that once you give the step input to the system, after some initial oscillations, the output of the system finally becomes equal to the input, because the input is actually the desired output from the system. So the servo problem is that your steady state output is equal to some reference input R, which basically means, because your y is equal to cx, it means that your states at the steady state are equal to the reference input R. And what does the steady state imply? The steady state implies that x dot is equal to 0. There is no variation in x, which implies that at steady state axs plus bus equal to 0, because x dot is equal to ax plus bu, and this x dot is equal to 0 at steady state, and at steady state your x is xs, so you have axs, and at steady state the input is us, so you have us is equal to 0. So basically, let me try to summarize this. Your system is x dot is equal to ax plus bu, y is equal to cx, and at steady state the xt variable becomes xs, the ut variable is some fixed input that you are giving in order to put the system at us, and the yt is actually the value of that you want the system to have at steady state, which is equal to some reference input r. So this is the steady state behavior of the system, and from this you automatically get, because your x dot at steady state would be equal to 0, so you get from these two equations you get axs plus bus equal to 0, and you get cxs, which is equal to cxs is equal to y is equal to ys is equal to r. So these two equations would help us in trying to find out how to track some reference input at steady state. Instead of all the states becoming 0, how to track some reference input at steady state. Now take shifted variables, and we'll see that this problem is very similar to the problem of regulator design that we have done. So we change some variables here. We define new variables. We define a u tilde, which is equal to u minus us. We define an x tilde is equal to x minus xs. This is not the x tilde of the aerodynamics. I'm using the same symbols because these are the symbols used in the book. Otherwise, I would have used something else. But in order to avoid confusion, take a shifted y equal to y minus r. This u, x, and y are from the original system, and these are us, xs, and r. Us is the value of the input at steady state. Xs is the state variables at steady state, and r is the reference input that we want to track. So let us look at x tilde dot. X tilde dot is going to be equal to x dot, because at steady state xs would be constant. So when you differentiate on both sides this equation, you get x tilde dot is equal to x dot. Now let us look at ax tilde plus bu tilde. This is going to be a u minus us plus a x minus xs plus b u minus us, which is going to be ax plus bu minus axs plus bus. And since we already know that axs plus bus is equal to 0, this is going to be ax plus bu, which is going to be equal to x dot, which is equal to x tilde dot from here. So for your shifted variables also you have this equation, ax tilde dot is equal to ax tilde plus bu tilde. And the second equation, y is equal to y tilde is equal to y minus r, y tilde is equal to y minus r. You can write this as cx minus cxs, because you know that your r is cxs and your y is cx. So this is going to be cx minus xs, which is going to be, and x minus xs is x tilde, so y tilde is equal to cx tilde. So the second equation is y tilde is equal to cx tilde. So these are your dynamics in the shifted variables. Now in this shifted variables, assume that you are able to design a control law. U tilde is equal to minus kx tilde, such that x tilde t tends to 0, right? And y tilde t automatically tends to 0, in the sense that you have, for this shifted system, designed a control law given by this, such that for any initial condition the states tend to 0 and the output tends to 0 and the system stabilizes. This automatically ensures, when you say that this x tilde tends to 0 and y tilde tends to 0, this automatically ensures, because x tilde is x minus xs and y tilde is y minus r, that xt will tend to xs and yt will tend to r automatically. So when you design a state feedback law for this system, which is given in the shifted variables, and the state feedback law is given by u tilde is equal to minus kx tilde, you ensure that your original system is such that it tracks the reference input at steady state. So the control law that you have to implement is u tilde is equal to minus kx tilde. Now let us try to put this back in the original variables. This u tilde is equal to u minus us, and this x tilde is x minus xs. So in the original variables, the state feedback law is going to be minus kx plus us plus kxs. So this is the state feedback law that you have to implement in order to ensure that your output tracks the reference input. Now let us try to simplify this further. Take the original equation, 0 is equal to axs plus bus, and in this original equation let us add and subtract bks. So you add bkxs and you subtract minus bkxs. So you get 0 is equal to a minus bkxs plus b us plus kxs, and from here you'll get xs is equal to minus a minus bk b us plus kxs inverse, sorry. So basically you can write that your us plus kxs is equal to, okay, before that let us multiply this with c. So you get cxs, which is equal to r, is equal to minus c a minus bk inverse b us plus kxs. So you can write your us plus kxs as minus c a minus bk inverse b inverse into r. So you can write us plus kxs is equal to nr, where your n is minus, where your n inverse you can write as minus c A minus BK inverse into B. So now you can use the substitution for US plus KS KXS that you found in this feedback law that you actually obtained. So your state feedback law U is equal to minus KX plus US plus KS, which is plus NR. So the state feedback law U is equal to minus KX plus NR, where N is given by this, and inverse is equal to minus C, A minus BK inverse B, ensures that your YT will tend to R as T tends to infinity, or as the system tends to the steady state. So basically you have added one more term to the state feedback law, and if you look at the shape that it is going to have, is that you have this system x dot is equal to ax plus bu. You took this x out here, then you multiply this with c, you got your y out here, took this x, multiplied this with minus k, and then what you're doing is basically this is a part of your state feedback law, and another part is coming from the reference input that you're providing. So your state feedback law here, U is equal to minus kx plus nr, and when you calculate n the way it has to be calculated from this formula, what you're ensuring is that this y would actually be tracking this r at steady state. So I hope this is clear. So this is the end of the third unit, end of unit 3. After this I'll be uploading a small tutorial on the third unit, and once you finish the tutorial we'll be taking up the unit 4. Please feel free to talk and interact in case you feel that something is not clear. Thank you very much for listening.